Good morning, everyone. So today we'll be talking about the first phase of contaminated site assessment, remediation, and risk. So let's lay down some ground rules before I get started. If you have any questions, feel free to ask. Feel free to interrupt me. If you think I'm going too fast, make me stop or make me go slow. If you think I'm going too slow, well, then bear with it. I guess then yeah, be with me, interact with me, ask me questions. If you have a comment, I'll welcome that. If you have a case that you want to talk about, something that you felt has happened in your neighborhood or in your life as a professional, I'll welcome that. Let everybody learn from that experience. Okay? So I want this class to be very animated. So feel free to ask. If you have anything that you think we would like to ask or talk about, but you don't want it to be video recorded, all right, let me know. I just made an arrangement with him that we'll stop the video and take it offline. All right? But I want you to get as much as you can within this 5-day period. This particular course is, I teach a course on contaminated site remediation. I teach a course on contaminant transport. I teach a course on water and wastewater treatment. I teach a bunch of other courses as well. So there's a lot of information that swirls in my head. Okay, so I might be jumping from one thing to the other. Feel free to interject and ask me questions. If I have to stay longer, I'm happy to do that. My only problem is my throat should hold, but other than that, I'll be happy to stay longer if you think I should. Okay, but try to get the maximum out of me during this next few days. One thing I don't have is time. Otherwise, I would have been happy to spend another week with you guys here. All right. So with that little introduction, let's get going here. Okay. So what are the environmental pollutants and what are their significance? So environmental pollutants are chemicals that are released to the environment by human activities. Okay. Once something exceeds a particular criteria, it is called as so-called pollutant. Now remember, we talked about heavy metals in the break before. They're all naturally occurring elements. They're all there. But if something is above background and introduced by an anthropogenic activity, a human activity, then it generally classifies into so-called pollution, or we have created a pollution. Okay, something that's caused by a human activity and has risen above the level the criteria at the background. Okay, they're harmful to human health and the ecosystem. Can you see from there, or is it too light? Huh? Do you want me to switch off a light here? This one probably. A little better, right? Huh? Thank you. So the environmental pollutants pose threat. There are 3 aspects of it, okay, that we need to understand and identify. Number 1, which we all understand, is toxicity. It is toxic, right? Which is the biological response to chemicals, and then the pharmacokinetics, or the absorption of it. So if this particular glass of water has got, let's say, a certain thing, let's say lead, okay, the lead, I'll take it in, then it will be absorbed by through my body system, and then the lead will get distributed into the bones and this and that, right? Now every person has a different threshold of tolerance, should I say. Like kids, Lead is especially a neurotoxin for small children because they put the hands in the soil, put the hands in the mouth, it goes directly from the soil to the mouth. As adults, we don't do that. So the impact of lead pollution is much less on us. Lead is a neurotoxin. So for kids, because they are at the developmental stage of their brain, the brain gets impacted quite a bit. So lead, if you have lead pollution, it's specifically a significant problem for kids compared to adults. Okay? So there is toxicity, and we'll talk about toxicity more. But on the environmental side, there is something known as an environmental persistence. Okay? Some of these contaminants don't degrade. Okay? A good example is, can you give me a local example? Polythene, but I wasn't thinking of that. Yes, give me another one. Louder, huh? Pesticides, yes. What about DDT? The one which you use to control the mosquitoes, right? A big one which actually remains in the environment for decades. Okay? Pesticide, linden, all kinds of pesticides, not only linden, atrazine, a whole bunch of them are there. 2,4-D, which is used for controlling, it's a herbicide, and so on, right? So the persistence, PCBs, for example, polychlorinated biphenyls, was used extensively as a coolant, not coolant, as a thermal stabilizer in transformer oils, and because they gave the thermal stability of the chemicals, they are very stable. See, one of the things is most of these companies, when they develop these chemicals, they develop with an intent. Okay, so the chemical companies, the managers will say, we got this problem of this oil breaking down when you are heating because it's high temperature. You are a chemical engineer. Can you devise something that can actually make sure that the oil does not break down at high temperature? Right? That's how R&D works in a company. They have a problem, they want to fix the problem. So all these chemical engineers get to work and they develop something that is thermally stable, that gives thermal stability to the, let's say fluid at high temperatures. But they do a good job, and now it's a problem for us. If that thing had broken down, it wouldn't be as much of a problem for us. But these things were designed with an intent of not breaking down, and therefore they don't break down in the environment and become persistent. And that's one of the other issues with environmental pollutants, is the persistence. And the third one is the bioaccumulation. It is the process of accumulation of chemicals through the lungs, gills, gastrointestinal, and dermal. So, and it can be several orders of magnitude higher. I'll talk about bioaccumulation pretty quickly here. So, what are the factors that affect? So, bioaccumulation is something that is accumulating in my body. So, let's look at this particular. Let's look at this. You know, these chairs are a kind of a pain here. Okay. Don't worry, I can take care of myself. Don't worry, I'm used to doing everything myself. Don't spoil my habit. So look at this scenario. Let's say I drink a glass of contaminated water, okay? And let's take its contaminant with, we are talking about this example of lead. Let's say it's got small amounts of lead, okay? What happens? I drink the water, the lead is scavenged out of the water very effectively by my body system, taken into my body, stored in the bones and wherever else, okay? The next glass of water I drink, same thing happens. The third glass of water I drink, same thing happens. Over a period of 5 years or 10 years, if I continue drinking that, what will the lead concentration in my body be? It'll be a lot higher than what is present in the water. You bring somebody in to test the water and they say, it's not much. Because it is not much. But the very fact that I've been drinking it for the last 10 years, my body will have a much higher lead content than what's present in the water. You might say, okay, it's about one part per million or half a part per million or whatever, right? It's very and that, but if you actually do a tissue test on somebody like myself who has been drinking that water, it is now probably 100 ppm, okay, 100 times or even higher. So that's what is this whole area of bioaccumulation. Environmental persistence, because it doesn't degrade, it's going to be there. Lipophilicity is basically fat attraction, attractiveness to fat, which makes it hydrophobic. There's a whole bunch of organic chemicals that are hydrophobic. Hydrophobic means hate water, okay? They hate water, so they will be present. They're lipophilic or fat loving, right? So they love the fat, so they'll have a tendency to get absorbed by the human system, right? And then there's something known as biotransformability. Biotransformability is once it is absorbed into the human body, the chemical may undergo transformation. My biological system is also a biochemical system, right? My whole body. So there are things like pH changes, and there is fat and all that. So within that, the particular organic or so-called pollutant will get fixed in it. And once it gets fixed in it, because of the microenvironment that is present, they might undergo some change, right? And sometimes it works to the benefit. They become more water soluble, right? The biochemistry might make it more water soluble, in which case it might get flushed out, okay? But by and large, it does get fixed somewhere. So bioaccumulation factor is the concentration of a chemical in the tissue of a target organism divided by the concentration in the diet. Okay? So these are some of the terms: bioconcentration and bioaccumulation. Bioconcentration is the uptake of aqueous toxicants through gills and epithelial cells of aquatic organisms. Okay? Bioaccumulation is slightly different. Uptake of toxicants from different sources, including bioconcentration. The dangerous one is biomagnification, process that increases the bioaccumulation as one moves from producers to predators. So let me give an example of let's say DDT. So it is a hydrophobic material, it's water. Okay. So in a lake, where will you find the DDT? In the किनारे, नीचे किनारे पे sediments in the sides, whatever, right? Because it doesn't like the actual water body, so the dissolved phase might be low, but it will be accumulating in the sides, right? Sides meaning in the sediments, in all that, right? That particulates that might be present. So now you have all these small little benthic organisms in a lake or whatever, right? And these little benthic organisms are eaten by the small fish. Okay, so the DDT, so look at it, the DDT now partitions on the benthic organisms, and those benthic organisms are a diet of those small fishes. 10 of those small fishes are eaten by a big fish every day, roughly, right? So now all those DDT from those 10 small fishes are now accumulating onto the big fish. Okay, the fishermen whose primary diet is fish will then eat maybe one big fish a day. Okay, so and at every stage it is multiplying. Okay, which means now if you take the human system and compare it with the water and say, okay, नाले का पानी तो it doesn't have as much DDT, थोड़ा सा है 0.1 ppm, but that 0.1 ppm at every stage has gone up, and by the time it lands in the person, you can get a bioconcentration factor thousands and thousands higher than what is present in the water. Okay, so that's the severity of the problem in this case. So I think the DDT bioconcentration factor is 73,000. So bioconcentration factor is basically, this is a differential equation. Don't get worried by differential equations. I'm not going to use it to solve it, but I just want to illustrate how this thing works. This is the concentration in the water. That is the concentration of the toxicant in the organism toxicant residue. dF by dt is the rate at which the toxicant absorbs, and here is in a steady state, which is you would find that the amount that is present in the body is some factor multiplied by the concentration that's present in the water, right? So if you have a number which is 100,000, which is not which happens many times, so you will have BCF of 100,000 multiplied by the concentration of the water. So even if you find 1 ppm or 0.1 ppm or 0.01 ppm, you are looking at tens of ppm to be found in the person who's taking it. So that's how the bioconcentration and bioaccumulation actually work. That's the thing that makes environmental pollutants so dangerous. Okay, so of such concern. Okay, so bear that in mind. So when you have lakes and rivers and all that with all kinds of problems, water, that's what happens when, and that's why people have this. You may not be able to backtrack it back based on our current understanding unless we know something around this. Why are people falling sick? We may not be able to backtrack it back unless you know that there is a bioconcentration happening, because by looking at the water or the sediment, you may not be able to get to that. There is also good correlation between KOW. You know what KOW is? How many of you know what KOW is? The octanol water partition coefficient. Feel free. Does anybody here want to take a stab at what KOW is? Okay, good. I need to know, because if everybody says I know it, then well, what the heck am I talking here, right? So KOW is the octanol water partition coefficient. What it means is it's the measure of the hydrophobicity of a particular chemical. So if you have a chemical, what you do is, it's a very simple, half of a jar is filled with octanol and half of the jar is filled with water. Put the chemical in it, shake it well, find out how much of it is in the octanol, how much of it is in the water. The ratio will tell you whether it loves water or hates water. Okay? Something that hates water will partition onto the organics. So this is the bioconcentration factor. That one is a function of the octanol water partition coefficient, which means higher the octanol water partition coefficient, higher the bioconcentration factor. Makes sense? Right? Something that hates water partitions more onto octanol. Something that partitions more onto octanol actually will partition more into our bodies, because our bodies are organic, right? There is this flesh and fat and all that stuff. So you can see that, and there are different relationships that exist, but these are two example relationships. Okay, so and also the chemicals that bioaccumulate resist degradation. Okay, so keep that in mind, that this is a very insidious way of how you fall sick. There is no direct correlation. Your water is polluted, you drink, you fall sick. That's acute toxicity, right? But this kind of a chronic effect, what we are talking, and I'll talk about that in a bit here, toxicity. That's the other thing I wanted to talk about. What is toxicity? When you say, okay, this is toxic, what do you mean by toxicity? What do you mean by toxicity? It affects the body. Okay, let's be a little bit more specific. Huh? Presence of heavy metals. So if I have heavy metals in this glass of water and I choose not to drink that water, will it still be toxic? So the very fact that it is present in the environment doesn't make it toxic. Remember, they're all natural. We don't create chromium and lead and all that. They're all naturally occurring. As long as there's no pathway for it to make into my body. So yeah, I heard somebody say something. What is toxicity? Okay, so toxicity is defined, there are three stages of toxicity. There's acute toxicity, there's chronic toxicity, and there is subchronic toxicity. Acute toxicity is something, I drink this, it's got some giardia or cryptosporidium or something, I fall sick, you get the usual sickness, high fever, nausea, vomiting, diarrhea, all that stuff, cholera. They are all examples of acute toxicity. It happens within 4 days, you will start seeing the impact of it. Okay, that's acute toxicity. And the way we quantify acute toxicity is understanding what is known as the LD50. You know what LD50 is? Finish that sentence. No, lethal dose that kills 50% of the fish or whatever is your target, right? So that's the lethal dose that kills 50% of the fish. That's LD50, right? But think about us as environmental engineers. What does that mean? If I take a glass of, let's say a bowl of water, right? And I put some experiment, I find that at this dose, 50% of the fish are killed. What are you going to tell people? Will you tell the people to drink this water? No. Okay, what are you going to tell the person? That's the answer the public wants. What are you going to tell persons? You cannot tell anything. What are you going to tell? 1/10 the amount? You don't know. That number is high here. 50% of whatever is your target is dead. You're not talking about people dying. You want people not to have any impact. And when you say any impact, you mean no impact, not even a headache to even the most sensitive subpopulation. We should not be considering ourselves as full-grown adults as our target. Our targets are things like small children, babies, seniors or older people, people who are immune compromised, who have some sickness or illness. They should be able to drink that water without having a second thought, right? Expectant mothers you don't want the babies to get impacted. So your desire is here. This is my level I want to be at. Right? Whereas the number LD50 is giving you 3 orders of magnitude higher, right? So there is the problem of measuring acute toxicity. Then there is something known as a chronic toxicity. It's a toxicity as a result of long-term exposure to a toxicant. The typical 3 that are talked about are carcinogenicity, which is cancer-causing. Long-term exposure at low dose leads to cancer, right? We know there are some chemicals like that. Mutagenicity. What is mutagenicity? Right. Can you give me an example of a mutagen? Huh? Will change the DNA? So if somebody takes chromium, radioactive is a better example, right? I mean, yeah, it might be, but because it is mutating the gene, so you will see that in the next and the next and the third generation. There is something known as a teratogen. What's a teratogen? Right, so teratogen is something that impacts the direct next generation, but doesn't actually mutate the genes. Can you give an example of a teratogen? Yeah, give me more. Just carbon particulates. Don't think that much. It's a very simple example. It's a very simple example. Huh? Hydrates. Nitrates. Blue baby syndrome is one. Something that we normally take when we go out on parties. Alcohol. Fecal alcohol syndrome. Right? A very good teratogen is very good in the sense, good example. It's not a good anyway. A good example of a teratogen is thalidomide. Are you familiar with thalidomide? Thalidomide was a drug given, and sadly enough, it was given to expectant mothers in the early 60s, late 50s, to control their morning sickness. And thalidomide is a dangerous teratogen. So the children that were born, they're actually known as thalidomide kids. They have deformed legs, deformed hands. They usually don't survive for the first 10 years of their life. Really severe deformities. In fact, if you see a person with such severe deformities of that age group, maybe 60 or so, 55, most of them are dead. But if you see them, then that's probably a thalidomide kid. It's really sad. It was banned globally for a long time, until very recently they have started putting it back as a treatment for leprosy under extremely controlled conditions. And there has been some controversy around that because of this massive history of thalidomide. So that's an example of a teratogen. So there are many teratogens as well. So the carcinogen, mutagen, teratogen, those are some of the ones that can cause, because of tonic, this thing. They are measured by endpoints. Endpoints is like what's happening. And there are some things known as NOL. Now these are acronyms you should be familiar with, okay? If you want to practice as an environmental engineer, if you want to be an environmental engineer, you know what, I need to put this one somewhere. Can you hear me? As clear as before? Okay, great. You have to familiarize with these acronyms. You also have to familiarize with some numbers. Numbers in the sense, you should be able to relate when somebody says this is 30 ppm. You should be able to relate whether 30 ppm is too high, is too low, right? Like 30 ppm of calcium in water is not a big deal. 30 ppm of lead in water, now we are talking about real problems, right? So you should be able to relate some of these numbers, okay? And that's so, that will distinguish you from where you land in work, okay? Can we stop the video for a second? Okay. Things to be but this is how you need to understand this. So NOL, what it means is no observed effect level. NOL is no observed effect level. So how do you think? So let me give another example. Let's say you are working in a health regulatory body, okay? And your boss comes in and says, I'm hearing this thing about chromium. Who's working on chromium here? You are, a couple of people, right? So he says, I'm hearing about chromium. We need to do something about coming up with a guideline for chromium. Okay? What will you do? Chromium in drinking water. So let me rephrase the question so that everybody is clear. Let's say you're working in a health regulatory body, okay, which monitors the drinking water quality and all that, okay, making sure that it's safe for people. And your boss comes and tells you that, I'm hearing this noise, people are talking about chromium in water and some people are falling sick. We need to do something about this. We need to come up with a guideline for chromium. What will you do? How will you now go? And you may have maybe a few minutes to ask the boss a couple of questions, but he leaves the room, he or she leaves the room. What will you do? You will go to literature. First thing is you'll look at Google and see what are toxicologists saying about chromium, right? That's what you will do. So if you look at the toxicological literature, they will have these acronyms. They will conduct tests on mice, on hamsters. They will say 10 hamsters I studied and I found the NOEL, which is no observed effect level. No observed effect level, which means that there's no observed effect. There is a NOAEL as well, no observed adverse effect level. How they define adverse is up to them. There is a LOL. What happened? There is LOL. LOL is low observed effects. Again, low is again how they define low. So you will come up with all these acronyms. NOAEL is no observed adverse effect level. LOAEL is low observed adverse effect level. क्या वो कट गया क्या? Okay. Okay. So you will look into this. If I want to complete that story, because I don't want to leave that thing hanging, how will you go about? So you said you're going to look at literature, right? And you come up with all this. Then what are you going to do? Source of what? No, you need to find a criteria. You need to find a number which is acceptable. What will you do? You're not finding a source. Your boss has told you, I'm hearing about chromium. We need to have a national guideline for chromium. Huh? A permissible, it's called acceptable limit, by the way. It's not permissible, it is accepted. We accept it, we don't permit it. Okay? There's a difference in the meaning. We tolerate it. Sorry, we don't even call it acceptable, we call it tolerable. We tolerate it, but does not mean we accept it. Just so that, anyway. So how do you find the tolerable daily limit? Okay, so yeah. You will have to do a full-blown risk assessment. The first thing you need to do is to find out what the NOEL and the LOL is. Again, those are high numbers, like 13 hamsters had brain tumors. Big number, right? You don't want, it's a big thing. So then you'll put safety factors, and you divide by a number of safety factors and eventually come up with some kind of a number. Find out whether it's a carcinogen or it's a non-carcinogen. Whether it is how severe is the effect. If they're saying it's brain tumor, then you're talking about big things. If they're talking about maybe not that severe, then you have to have a whole series of so-called uncertainty factors that has to be built in there. Okay, so from there on, you actually translate a chronic toxin into a TDI, which is a tolerable daily intake. Anyway, I digressed a little bit. So processes that affect subsurface behavior of contaminants. What is it that actually causes contaminants that affect the behavior? Now, so I told you that some things which are hydrophobic. So which is worse, hydrophobic or hydrophilic? Hydrophilic dissolves in water, hydrophobic is water hating. We have established the definition. So which is more harmful, hydrophobic or hydrophilic? How many of you say hydrophilic? Okay, there's like half, and the rest of you think is hydrophobic? Is there anybody who thinks that was a bad question? That was a lousy question. Oh, there it is. We have a winner. Yeah, it was a lousy question. It doesn't look. I'll tell you, hydrophobic is bad in the sense that it gets absorbed in the body, so faster I'll take it out from the water. But hydrophilic is bad in the other sense that it translates further, right? Dissolves in water like salt. It dissolves in water, now it's gone like 5 kilometers before you can blink an eye, and now it's a problem for the entire neighborhood. Plus the toxicity is not defined. You can have really toxic hydrophilic material too. So yeah, you can't don't try to guess that based on the hydrophobicity or hydrophilicity. So the processes, so hydrodynamic process, advection, dispersion, preferential flow through cracks and fissures. So who's going to tell me what is advection? What is advection? What is advective flow? So when your river flows, when water flows in a river, there is a flow that is happening because of velocity, right? River is flowing, there's a speed in the water, it's flowing, right? That's typically advection. Flow because of the velocity itself. What is dispersion? Movement because of heterogeneities in the media. So if I have, if you look in the subsurface below the ground and you have this, and I magnify it, let's say you got these two sand grains, okay, and if the flow is happening in this direction, there is a path that flows like that, right? Okay, that is the typical speed pattern. So between the two sand grains, the speed is highest, and close to the sand grains, the speed is lower, right? So when the speed is highest, what is the particle doing? It is dragging the particle behind it to move fast, right? Conversely, the one behind it is pulling it back. It's like two particles, one moving faster, one moving slower, and they're dragging each other, okay? And similar now, and if you have in this one, let's say another sand particle here, a third sand particle here, fourth one here, the water will flow like that, right? So it is moving in that direction laterally, right? That is dispersion. That is known as dispersion. The fact that it is mixing, moving in directions that you, in other directions, right? It is called dispersion. I'll give you an example. Let's say you have you're carrying a bag of salt across a river, and across a river, and you happen to drop the bag in the river. Just plain sodium chloride. Now, if you have a monitoring down the river for let's say 5 kilometers down, will you find salt in the water? You will, right? Will you find salt all around in the water? You deposited it as a bag, as one location, but you will find all over, right? The fact that it has moved all over is because of dispersion. There is velocity driven, which is advection, but the horizontal part is dispersion. Are you with me on that? Then there are cracks and fissures. Soil we know is cracked, right? There are cracks, there's fissures, there are roots, all kinds of stuff. The water will make their way. So it's preferential. It's going across from cracks and all that, right? Then there are things that like abiotic processes, which are adsorption, precipitation, volatilization, ion exchange, hydrolysis, redox reactions are all reactions that continue to happen in the system when you are, as the water is going. So when a groundwater is contaminated, so let me back up and ask us another question. Maybe a silly one, but let's get there. If you have a contaminated site, why do we need to bother about it? Why do we need to bother about a contaminated site? Right. So basically, it is a water problem, right? So this is also a thing to keep in mind, that when you have, for a contaminated site, it is either a water problem or air problem. Okay, and it is because of that you need to address it. So, but something happens in the groundwater, in the soil, but what has been deposited in the soil and what you find when you actually find the pollutant Might be two different stories. Okay, because you might find that some of those stuff that you put in the place, some of have volatilized and gone. So the lighter fractions have volatilized and gone. There might be some things that are, because of geochemistry, they might have precipitated out. They might have undergone hydrolysis. A whole bunch of reactions might have taken place. So what you may find, so the contamination happened like 20 years ago or 30 years ago, and they put something in the ground. But when you come back after 20 years, it's a very different. It's a different thing. So keep that in mind, that there are processes that go on in the subsurface that can actually transform it. And of course, there is biodegradation, aerobic, anoxic, and anaerobic, which can cause the contaminants to degrade. Aerobic degradation is something that degrades in the presence of oxygen. Anaerobic degradation is something that in the absence of oxygen, and anoxic is there as well. So zone, and this is a simple illustration of you got the what is at the top there. There is the land surface on the top that's poorly constructed. Figure there is an unsaturated zone on the top, and there is a saturated zone at the bottom. And I have written there, saturated zone is more important than unsaturated, right? Why am I saying the unsaturated zone is more important? Sorry, saturated zone is more important than unsaturated. Huh? Louder. Groundwater is there, and that's where the real problem is. So in the unsaturated zone, it will make its way to the saturated zone, but eventually it gets transformed in the saturated zone, and you pick it up from there. Okay, what are the different phases of contaminants? Okay, phases means in what form does it exist in the subsurface. It might exist as an adsorbed. So you got sand particles or particles like this, right? So you will have adsorbed phase. Okay, what's adsorbed? It's physically bound to the particles. Okay, they're not sitting in the water, they're just actually attached to the water, to the sun. What's that? Yeah, so it is attached to the surface. There is dissolved phase because it's, so you got the sand, not sand, I shouldn't say sand, I'll say soil particle, right? Because it can be any one. You will have the adsorbed phase, but if there is water in the pore, it will be dissolved in the water, right? It can be in vapor phase in that pore space, right? If it is unsaturated, there is water, there is air, there is solids. Okay? Are you with me on that? So it will be in the vapor phase in that pore space. It will be adsorbed onto the sand particles, and it will be dissolved in the pore water. And on top of that, it can be free phase. What is free phase? It's just sitting like a globule, right? Like a little globule, you may have the whatever. If it is oil, whatever, let's say gasoline or something is sitting there as a globule. All of that can be present in the pore spaces. Okay. So for contaminant remediation, you need to understand contaminant partitioning. What are the physical and chemical properties of the contaminant? Okay. How much does it dissolve in water? How much does it get adsorbed onto the soil particles? How much of it is, if there is any free phase present at all? What is the hydrology and hydrogeology of the geology and the hydrogeology of the subsurface? Like how deep is the water table, right? What is the geology? Is it clay? Is it sand? Is it lens? It's laterite? It's whatever, right? And the geochemical characteristics subsurface. In many ways, environmental engineering is a very complicated field. In fact, and that is why you would see people from many disciplines work together to solve a problem. When you go out and work in the industry, you would see that you will be working side by side with people with very different backgrounds. You'll work with biologists, you'll work with geologists, you'll work with chemists, you will work with environmental scientists and or environmental engineers. Depending on what is your background, you'll work with different people. Okay? You'll work with mathematicians and modelers, and so they have to come together because it's very complicated, like the geochemistry. It's a very difficult field to understand yourself if you are not on that geology, geochemical background itself. So what are the contaminant types and characteristics? You got organic, these are simple ones, organics, you got alkanes, alkenes, chlorinated solvents, aromatics, inorganics, the main concern being metals, hydrocarbons used in a variety of industries such as metal finishing, automotive and engine repair, dry cleaning, asphalt operation, dye manufacturing, food processing, and so on. These are some examples. There are lots and lots more. Dry cleaning, for example. What is the chemical that you use for dry cleaning? Have you gotten anything dry cleaned? Right? Have you ever wondered what exactly is dry cleaning? Huh? Louder. Don't be afraid, there's nothing, right? It's all live stream, so everybody in the country will know how much. Just kidding. So just tell me. Petrol. No. H2O2, peroxide. They use perchloroethylene and trichloroethylene as dry cleaning solvent. These solvents. So what do our little friendly dry cleaner does? It's a small shop, right? 1/3 the size of his room. He will take this little thing, he will do his dry cleaning, and what will he do? He will in his backyard, right? So this is not local, it's a global problem. This particular chemical was regarded as one of the top priority pollutants because of this. So such rampant is the pollution because of this chlorinated compound. Because the dry cleaner, the moment you try to catch, he's gone, right? And that's everywhere. They're not a big business that you can recover the money, and it moves fast. So food processing, dye manufacture, and so on. Aliphatic hydrocarbons, alkanes, alkenes, alkynes, and so on. And the aromatic side, you got carbon-carbon structure. Aromatic is basically, you got, what's aromatic? Aroma. Okay, so you got the benzene ring, right? So you got the 6. Huh? No, cyclic is cyclic. This is the 6 benzene ring, right? The very famous benzene ring. It's very difficult to break those rings because they're very stable. But there is this whole series of aromatic hydrocarbons which have carbon-carbon ring structure. There's ortho, meta, and para. Basically depends on where you have the other things attached. Huh? So it depends on where the additional this thing is attached. You have functional groups. The toxicity gets impacted by that. Okay, so that's what the then alkyl benzene, polyaromatic hydrocarbons or PAHs. Then the nitrogen and sulfur containing compounds, trinitrotoluene, atrazine, which is a herbicide, mercaptans, pesticides like malathion, mesolam. This is just a non-exhaustive list. It's not a complete list by any stretch, but this is just a view. So hydrocarbons, undergo microbial degradation. We know that to some extent. They are also known as NAPLs. You know what NAPLs are? Non-aqueous phase liquid. Right, light non-aqueous phase liquid and dense non-aqueous phase liquid. And what is the difference between the two? So they are on top of the water table, right? And the dense non-aqueous phase liquid, because they have a specific gravity greater than 1. So they have a specific gravity greater than 1, which is basically the sink in the water, and therefore, so which is a bigger problem? Why? Right, because if your water table, it can go inside the water table and go into the crack and fissure of way down, and then can be, then can continue to remain a source for a long time. Okay, so DNAPLs are a much bigger problem. They're not readily biodegradable, non-sorbing, and so on. Gasoline, one of the biggest pollutants in the organic phase is gasoline. You got billions and billions of liters of gasoline that is being transported across the country, right, in trucks and in trains and so on, and the derailments and truck, all that, right? And gas stations, all these gas stations, many of them leak from the tank below and eventually make their way into the. So gasoline is a complex mixture of volatile hydrophobic hydrocarbons, typically have carbons with the C4 to C12 carbon atoms. Why is it important to know the carbon atoms? Because the characteristic of the hydrocarbon is determined by the number. The lower the carbon number, the more volatile it is, the less viscous it is, and more naplish, L-napple, right? Diesel, on the other hand, primarily straight chain unbranched hydrocarbons, some minor aromatics like BTEX. BTEX is an acronym that's used for benzene, toluene, ethyl benzene, and xylene. Less volatile, heavier hydrocarbon than gasoline. That's why a diesel leak it takes a longer time to evaporate. Carbon atoms range between 8 and 27 for automatic diesel fuels, and so that's the diesel. But I come from a colder climate, and where and in that places when it's cold, really cold, you need the diesel to have an even higher fraction of heavier material for it to work. So that's known as, you see diesel fuels for railroads and bunker fuels have even longer chains. Okay, so then they add additives to make it, you see, have the cold start at minus 20 degrees Celsius. Okay, so that's, so diesel fuels have different varieties depending on where you are. Then there's motor oil and waste oil, carbon numbers greater than 20, heavy stuff, high molecular weight, less dense than water, relatively insoluble, and minimally mobile. They're not as mobile. Waste oil contains some aromatic hydrocarbons and some PHs. Chlorinated solvents and degreasers. The chlorinated solvents is one of the biggest problems. So the biggest hydrocarbon pollution comes from gasoline. Okay, because look at the amount that we use daily, right, in our vehicles and all that. So gasoline and diesel comprise the largest amount. But from a problem perspective, the chlorinated part is a big one, is in fact, by some estimates, even bigger because of the cleanup operation that is required. Okay. Metals can enter via agricultural additives such as fertilizers, manures, herbicides, So common metals are chromium, cadmium, iron, lead, mercury, aluminum, nickel, copper, and silver. If you have silver, you'll try and recover it. So some of these you'll try and recover it. For example, silver, because of its value. The others maybe not. Municipal solid waste, sewage sludge, stormwater runoff, storm waste from mining and smelting. All of these. Okay. How far are we doing with time? 12:30. When did we start? We started at 1. That reminds me, where did I keep my iPhone? I just want to make sure I haven't lost it. Why don't we take a 5-minute break? Okay. Yes, we finished this, right? So let's move on to the next one. Contaminant transport. Okay. This holds, as Director Tripathi alluded here in his inaugural speech, there's so many different topics that come under this purview, and you must have peripheral vision. You must have an understanding of the others. Otherwise, if you work in this field and if you have a narrow vision, you'll get blindsided if you don't have. One of the things you should know is contaminant transport. Okay? How does a contaminant move in the subsurface? I'll go over it a little bit here, but you should learn a little bit more than what I can go over here in this day. Impact of geology and hydrogeology. So the transport of a particular contaminant is a function of or is dependent on the geology and the hydrogeology, the soil type and soil characteristic. If it's clay soil, it doesn't move fast, right? Clay soil has got a very low hydraulic conductivity, right, compared to sand. The texture, I mean, of course, they are related. Grain size distribution, right? If you we all know from geotechnical that what grain size means. Classification: clay, loamy soil, silty soil, sand. Geology of the contaminated site: how deep is it? How far is it? Okay. Depth to water table and aquifer characteristics. I know many of you are PhD students and probably aspiring to be academics, right? But also academic jobs are far and few, and some of you will land in the industry. And if you happen to do that, this course is designed with keeping that in mind, that you will go into a professional field or practicing, because even if you're in academics, you should at least know how this whole thing would work. So the reason for my telling you all this is site characterization is very important. Okay, most times the client will not be as willing to spend money on characterization, and you as a consultant or as an expert in this field will have to educate the client, because they don't see, okay, you're characterizing means you're studying, right? Studying means it's not solving their problem, right? You're studying this, it's not solving the problem. We come back after 1 year and say, okay, this is what it is, right? But the value that they get out of a good site characterization really repays them a lot on this remediation. Like when I ask for, okay, give me a sample, many times I get sample which is not contaminated, because they have sent a contractor on the site. The contractor has dug up some soil which is not contaminated, poorly characterized site, right? So look at the cost. They have dug it up somewhere in 4,000 kilometers away, 3,000 kilometers. Remember, Canada is a very big country. So put it in a truck with all the precautions, send it to my lab, and I do an analysis. My time, the trucker's time, everybody else's time, but to what avail, right? So That's what. So, but that's just my example. If they're cleaning up the site, you'll be cleaning up clean soil. If you have not poorly, if you're poorly characterized, you might leave contaminated soil. So a lot of good time should be spent in designing what you are trying to clean up. And so keep this in mind if you're practicing in the field. Spend the time, spend the money, whether you are on the consultant side or on the client side. You should keep that in mind. A good characterization will actually save you money in the long run, because you want to only treat the soil that is contaminated. To treat that particular soil that is contaminated, you don't want to treat an uncontaminated soil, clean soil, because it is expensive. Let me tell you, it is not cheap. It is expensive to clean soil. There's no two words about it, right? So spending time and making sure you are actually cleaning up what is the problem, spending time and money is worth its worth. Okay, contaminant transport pathways, liquid migration through the vadose zone, spreads over the water table and stabilize within the capillary zone. You know what a capillary zone is? Right? It's the zone on top of the water table, right? Caused by what? Capillary forces, right? So is it higher in silt than in sand, or is it lower, the capillary rise? Huh? Is it higher in sand or is it higher in silt? What is the answer? Is it higher in silt? Higher in silt, right? Because of surface tension, right? Okay. So the volatilized vapor can be released to the atmosphere, excuse me, absorbed by the soil particles rather, consumed by microorganisms, redissolved in moisture and soil pores. Okay, now I will get into a little bit of numerics. When I said 1 part per million, 5 part per million, you guys are all familiar with it, right? What does that mean? No, what does it mean? 1 part per million, what does it mean? Just expand that sentence. No, what does that mean? It's 1 part in a million parts. That's what it means, right? 1 mg per liter happens because, now you say what you're trying to say. Why does it happen? Why is 1 ppm equal to 1 milligram per liter? Because the specific density, specific gravity of water is 1, and you can do the thing. Because of that, 1 part in a million parts translates to 1 milligram over 1 kilogram, 10 to the power minus 6. That's how it works. It just works out because of water. Keep that in mind. It works out because it's water, so it is valid only for dilute aqueous solutions. It is not valid if it is a concentrated solution where the density changes. All right? It is only valid for dilute aqueous solutions. 1 milligram per liter is 1 part per million. In air, what does it mean when you say 1 ppm? What does that mean? 1 microgram per meter cube of what? No. In air, it's again the same concept. 1 part in a million parts. Correct? The terminology you can't change. 1 ppm is 1 part in a million parts, right? So in air, it is a very different number. 1 ppm V, I call it V because volume, is molecular weight by 22.4 milligrams per meter cube. Okay, so in air it does not translate to 1 milligram per liter. It translates into this number here. Okay, so let me go through this conversion here, ppmv to milligrams per meter cube conversion. You remember your chemistry, 22.4 liters of a gas weighs 1 molecular weight at STP, right? So 1 liter of a gas is molecular weight by 22.4, 10 to the power minus 6 liters of a gas is molecular weight times 10 to the minus 6 by 22.4. Go through this. So 1 ppmv is 1 liter. 1 ppmv is 10 to the power minus 6 liters in 1 liter of air, right? That's what the definition means, 1 in 10 to the power 6. So this is what it translates into. 1 ppmv is molecular weight by milligrams in milligrams by 22.4 meter cube. Okay, I'm going to ask you this question. I want you to solve this question. You have it in your notes. A person drinks 2 liters of water containing 1 ppb of benzene and inhales 20 meter cube of air. Is that the numbers that you have? Okay, 1.5 is sahi, 1.5 karo. A person drinks 1.5 liters of water containing 1 ppb of benzene. Huh? 1.2 ppb, right? So I've changed the numbers here, but so I want you guys to solve that problem. I'm going to solve it here, but I want you to solve that problem in here. That's why I've changed the numbers from what is here. So let's look at this one here. 2 liters of water containing 1 ppb of benzene. What is 1 ppb? Part per billion, which is 1000 millionth, right? And inhales 20 meter cube of air contains 10 ppb benzene. Through which pathway is the person exposed to more benzene? Benzene ingested per day, 2 liters, 10 to the power minus 3, 2 times 10 to the power minus 3 milligrams. Molecular weight of benzene, 36 at 6, 78, sorry. 10 ppb, you multiply this. This number here, 22.4, changes to 24.05 at 20 degrees Celsius. And I made the assumption the person lives at 20 degrees and not at 0 degrees. So that's why this number will change from 22.4 to 24.05. So if you look at it, the benzene inhaled in 1 day is 0.648 milligrams, whereas the benzene that is ingested per day is 2 times 10 to the minus 3 milligrams. So you can say that the person inhales more benzene than he ingests. All right? Okay, was that clear? Was it clear or not? Okay. This is the mass of contaminants in different phases. Okay. Why do we need to know mass of contaminants in different phases if you want to remediate a site? Why do you need to know the contaminant partitioning? You know what partitioning is, right? Huh? Different forms, dissolved phase, vapor phase, whatever, right? Dissolved phase. Why do you need to know the partitioning of contaminants if you're trying to estimate the amount of contaminants in the why do you need to know that? So the moment you start putting a system in place to remediate, what is going to happen? Let's say you are doing vapor extraction. You are extracting all the vapors out. What's going to happen? All the clean air from the side will come in. Okay? And you will get the vapor out. But what will happen to the pore liquid that is present in the dissolved phase? There will be a lot more that will start to move into the vapor phase. Okay? Okay, let me back up here. I think this requires a little bit more explanation. So nature has a way of keeping everything in equilibrium. Okay? Let me give an example. Let's take this water bottle. Okay? Let's say this bottled water contains benzene. Okay? If I open this bottle, will I smell benzene? No? How many of you said no? If this water contains, let's say, small amount of benzene, if I leave it here, and I open it, will I smell benzene? Right. Why will I smell benzene? No. Why will I smell benzene? I just opened it and I'm taking a sniff. What? Huh? Why should it diffuse into the air? I've just left it there. Right, you are right. So just build that thought. Tell me, why should it diffuse? Because of the concentration gradient in the water and nothing in the air. That gradient will drive some of the benzene that is in the water into the air phase here. See, once I open this thing, I can smell it, right? So if I don't open it, what does it? So the amount of the benzene that is present in the concentrated in the dissolved phase here is in equilibrium with the benzene that is present in the water at the top, right? So, and if I leave, so it remains in equilibrium. That's nature's way of equilibrium. Okay. The moment I open it, now the benzene the air has come out, some of it, and replaced with fresh air, and you will now continue to diffuse it out, right? So now we talk about, I will come back to the question of why we need about in different phases in a bit here. So liquid gas equilibrium is described by Henry's law. Henry's law is a very simple law that states that the partial pressure of a gas above a liquid is proportional to the concentration of chemical in the liquid. See, if I have benzene in this one at, let's say, 1 ppm, there's a certain amount of benzene that will be present here. If in another bottle I've got 2 ppm, twice the amount will be present here. That's what Henry's law is saying. The partial pressure is a function of the concentration. Higher the concentration, higher the pressure. Or higher the concentration in the liquid phase, higher the concentration in the water in the air phase. Okay, that's what Henry's law states. If you go through all this, it says the concentration in the gas phase is proportional to the concentration in the dissolved phase. Okay. So coming back, so let me, so if I take this air, so I have no way of removing the benzene. I take this thing out, I run a fan over it, get rid of the air. What's going to happen? The benzene will move from the liquid phase to the air phase, and if I take that air and replace it with a fresh batch of air, clean air, benzene will move from here to there. And benzene will move from here to there. Eventually the benzene concentration in the water is depleting. Okay, it's a slow process, it is depleting, right? Now, that analogy is not 100% correct, because Henry's law is a static system. What I'm talking about is a dynamic system where you're moving out. But you understand what I'm saying here, right? The thing that so slowly and so this is why you need to know. Because if you put a system in place, and if you're removing the contaminant in a particular phase, once it is removed from that phase, the contaminant from the other phases will try to move into that phase to restore equilibrium. Are you with me on that? What did I do here? I took the cap, I removed the air, replaced it with fresh air. If that is my mechanism to remediate this water, is I will replace the air and I'll continue to replace the air. Okay, so I replace this little amount of air. Okay, and if I'm a novice, if I don't know what I'm doing, I replace this air and I say, benzene to chala gaya. Right? But 2 hours later, it's still moving from here to here. Okay? And I say, okay, let's do it again. Chalo, galti ho gaya, thoda ho gaya. I'll remove it and do it. I remove the water again, the air again. Again, I find the same thing. Okay? If I have budgeted a project based on my initial presumption that I'll take this air out and I will get the water clean, what will happen to me? Huh? My budget is completely out of whack. because the benzene will continue moving in this direction and I'll have to continue doing it. I don't have to remove this amount of air, I might have removed like 50 times this amount of air. That is why it is important to know the partitioning, because you might get blindsided if you don't have a good understanding of how the contaminant is moving. Because you will, let's say you have gasoline contaminated site, okay, you will pump the the air out. Once you pump the air out, all the gasoline that is in air phase will go, but the gasoline from the dissolved phase or the adsorbed phase will now start to get into the into the air phase, and the equilibrium will shift, and now you will have a continued phenomena in soil vapor extraction, which we will learn, I don't know, tomorrow or day after, whatever. You will see what is known as a tail effect, and the tail effect will completely blind you. You might be able to get the whole thing cleaned out within 10-15 days, but after that the tail effect line might last for 6 months, and if you have not budgeted that, you will be very short on budget and might even have to look for another job pretty quickly, because this will that might be the last job you will do if you make that mistake. Because think about it, 15 days you got the soil out, most of the vapor you can get out in a very short period of time, but after that the tail effect lingers on for months. Take an example of that thing. How long is it going to take to replace that air as compared to all the benzene from the dissolved phase coming out? Okay, that's why it's so important to. So this is the equilibrium between gas and liquid. Okay, here is another example. A groundwater sample bottle collected and brought to a lab at only 80 milligrams of water. This is exactly in line with what I have there in my bottle there. The benzene concentration in the water analyzed using a gas chromatograph was 5 milligrams per liter. I think your numbers are slightly different, right, in your notes. Okay. The concentration of benzene in the headspace, the percentage of total benzene mass in the aqueous phase, and the true concentration of benzene if headspace free samples were collected. If you want to follow me on this, I've got the solution here. So concentration of benzene in the headspace. Did you follow this question here? Anybody had any problem following this question here? Because okay, so concentration of benzene in the headspace is Henry's constant multiplied by C. Henry's constant 0.22 times C is 1.1. Concentration of benzene in the headspace, remember, is 24.05 because it's 20 degrees Celsius. Molecular weight of benzene is 78. So it comes out to 3.24 milligrams per meter cube. Mass of benzene in the liquid phase, C times V, 5 milligrams per liter times 0.08 liters. Mass of benzene in the gas phase, you got 0.022. Total mass of benzene, and of course the percentage of total benzene in aqueous phase. So this can help you in some ways by knowing this. So if you look at this particular problem, if you make a mistake, right? Let's say you collected a sample from the water from a river, okay? Now ideally you are expected to fill the whole thing, no headspace. But let's say you made a mistake or whatever, right? So your phone rang and started paying attention to the phone, whatever. You filled it only this much and came. Okay? Send it to the lab gives you a result. But the lab also writes that there was so much headspace that was left empty. Now you have the option to run back and collect another sample, or you can correct it using this Henry's formula. Right? Are you with me on this? Okay, the solid liquid equilibrium. The solid liquid equilibrium, so this is the adsorbed phase we are talking, is defined by two major philosophies: the Langmuir's philosophy and the Freundlich's philosophy. Can you tell me what is the difference between the Langmuir's philosophy and the Freundlich's philosophy? What is Langmuir's? Are you aware of this? Okay, so good. So here is the thing. Let's say this is a sand grain, my fist here, okay? Magnified sand grain. I can have adsorption, okay? Now, I can assume that there are specific sites in which adsorption happens. And if those sites are held, are occupied, then it's gone. It doesn't matter what is present here. Those sites are exhausted, right? That is known as the Langmuir's philosophy, okay? And the isotherm that comes out of it is known as Langmuir's isotherm, okay? The second philosophy is, I have got some sites, but they can attach itself. Think of it like little strands of hair, one after another after another. So you can have multi-layer adsorption, okay? That's known as Friend-Luich's isotherm. Both happen. We don't know which one happens. The Langmuir's isotherm is that equation on the top. The amount adsorbed is equal to maximum amount that can be adsorbed multiplied by a Langmuir's constant called KL times C, which is the concentration, plus 1 plus KL times C. Okay? That is the Langmuir's isotherm based on Langmuir's philosophy of maximum, that there is a maximum that it can adsorb. Okay? Can you show that? Can you look at that equation and show that there is a maximum amount that can be adsorbed? Which means X will reach a maximum value, which is X max, as C goes to infinity. I'll leave that as a homework for you guys. Try it. As C goes to infinity, X equal to X max. Okay? The Friend-Luich's adsorption of isotherm is the one at the bottom. Amount adsorbed is K, which is, it can be times C to the power n. If n is equal to 1, then you have a linear adsorption isotherm. A equals to Kd times C. And so it is pretty difficult to tell which is valid. Okay, to find out which one is valid, whether it is Friend-Luich's or Langmuir, you would actually conduct an experiment and then run through these two equations and see which one is more applicable. That's the only way you can find it. Okay, but for organic compounds, there is a little bit of a shortcut. Okay, the shortcut is that if you want to use this one here, you only need the Kd, right? If you only need the Kd, organic compounds, what did we say? Like to partition onto organics, right? So if you assume that the adsorption on soil minerals is 0, so if you take the soil and if you find out the amount of organics that is present in the soil, how will you find the amount of organics that's present in the soil? How will you find the amount of organics that's present in the soil? How will you find the moisture in the soil? Louder. Compaction. Did you say compaction? If I give you a soil sample and I say tell me the moisture content in the soil, how will you find the moisture content? Okay, so right, so you oven dry it and then WW by WS, right? Weight that is loss. How will you find the organic content in soil? Why can't you do the same? Huh? Retain muffle furnace at what temperature? Right, somebody said 550, great. Anywhere from 450, 550. So what you do is you first remove the water. Then you get the actual soil content with the organics. Then you take it, you stick it in a muffle furnace at 450 degrees Celsius, see the difference. It's pretty easy. Within a day you can find the organic content. So if I know the organic content of the soil, that's what this one is, FOC. Okay? KOC is organic carbon partition coefficient, which, remember, we talked about the octanol water partition coefficient, is a function of the octanol water partition coefficient. This KOC is a function of KOW. I can put my KOC, I can measure my FOC quickly, and I can get my KD, and if I want to use a linear isotherm, I can get my X without having to conduct any of the experiments to get the Langmuir's or the Freundlich's isotherm. But valid only for organic compounds. This is another example that will illustrate what I'm just saying. An aquifer is contaminated from a xylene spill. Okay? The groundwater contains 250 parts per billion of xylene. Estimate the concentration of xylene in the soil, which has 2% organic carbon, assuming linear adsorption isotherm. Okay? So log KOW of xylene is 3. I got it from tables. I picked up this equation that's valid for xylene. Log KOC gives the KOC value, which is in antilog of this one, 1021. KD KOC times FOC, I measured the FOC 0.02. I got my KD, I can get my amount. So I can tell that the amount adsorbed is 5.1 milligram per kilogram. Okay? So I didn't have to do anything. I just needed to measure the FOC. Right? It's a simple experiment. One day to get rid of the moisture, another day to get rid of the organics. I can do the measurements. May not be 100% accurate, but heck, we are talking about soils here. Everything is different from one location to the other. You at least have a good number, right? Valid only for organics though. Okay, so partitioning of contaminants in different phases. So we learned liquid gas equilibrium by Henry's law. We learned solid liquid equilibrium by both Langmuir's and Freundlich's adsorption isotherm. Now I'm putting everything together. Partitioning of contaminants in different phases, mass of contaminant, soil moisture, V times moisture content, porosity held by water times C, mass of contaminants in the soil grains, MS times X. You add the two together, and so you add the mass of contaminant in the soil moisture, in the soil grains, in the pore spaces. You add all of them together, and now you can come up with this. So the moral of the story is, apart from knowing this formula, is look at this formula: mass of contaminants per unit volume of soils. If I take a meter cube of soil, that's the amount of contaminant that is held in all phases, excluding the free phase. And we can't tell the free phase, right? That's just, if there's free, then there can be any amount. But if you want to know the adsorb, the dissolve, the air, all that, you can get all that, mass divided by volume, this whole thing multiplied by constant. So if I take a water sample from the soil pores and I measure the concentration, look at this: pore water, or porosity held with water, dry density, Kd, which is constant, porosity held in air, K, which is the Henry's constant, times. Okay, all of this is soil characteristic. So I don't need to go and measure what's in the dissolved phase, what's in the air phase, what's in this phase, that phase. I just need one phase, a formula, and I'm done. So this is an example of a problem again. The concentration of benzene and pyrene in the vadose zones are 200 ppm V and 10 pp BV. Porosity in the vadose zone is 40%. 25% of the pore space is occupied by water. Soil dry density is 1.8 grams per cc. Find out, calculate the contaminant levels in soil. So this is in your notes. You should be able to solve it. Okay? You have it in your notes, right? So try solving it. Okay, I am at a point of break here. Break means in the sense that I can stop here. Professor Singh, what would you like me to do? I can stop here and then continue from here. Stop here and continue. because it'll take me another 20 minutes to continue on. So I know you're waiting. So if you want, I can stop and continue tomorrow, or I can go on, and it's your choice. I am running behind. They have to take their lunch? What about me? What about my lunch?
No, these people.
No, that's what I'm saying.